All right, boys and girls, welcome back to the drive-through. Okay, for a wild, difficult version of the drive-through, sponsored to you by the deli. Hungry? Stop by the deli and get anything that Chris Seeger wants to make for you. I made my kids just pretty much the total run back of the Chris Seeger grilled cheese yesterday. I went to my little local bakery and got some sourdough, and my daughter said, she never says this sandwich is really good, Daddy. She never gives me any props. So I told her to give you thanks, Chris. All right, so look, you're going to have to totally think, okay? This is very difficult to comprehend, but it's where we're at right now, so you're just going to have to stick with it. The weird thing about this is we're trying to get to something that I think might really interest you, and that's like, well, let's say some particle is traveling through a magnetic field or through an electronic field, and that field varies, okay, as they do. What kind of force does that particle get exerted or exert on the natural world? But in order to understand it, we're going to treat all of these line integrals. Now, first of all, that's a misleading term. They should call them curve integrals or path, P-A-T-H, path integrals, okay? Because what we're kind of doing is saying, let's say that these paths represent a wire with a uniform radius, like of a radius of 1 unit. So kind of like a planar lamina, but a one-dimensional planar lamina. And let's say that over that path, the density changes. How can we find the mass of the wire? Okay? That's what we're doing. We are literally doing density times length to get mass. But eventually, the density won't be density. It will be something that involves electric fields, force fields, velocity fields. Okay? And the path will be length. So the length won't change. But what that function represents is what's going to change, and that's where it's going to involve your engineering. So the first thing we need to do before we get started is go back to something we once did, and that is assign a piecewise smooth set of parametric equations to this path. Okay? So as what we got here is this is C1, meaning the first curve. This is C2. And then here is C3 going up, okay? So as t goes from 0 to 1, this is the easy version because it's starting at the origin. So it goes from 0, 0, 0 to 0, 2, 0. So what does x equal the whole time? 0. Y is the thing that depends on t. So it's 2t. And z is 0. Okay? I'll take questions. No problem. I'm just going to pause the video. Okay, now, first, this is C1. Not to be confused with our fabulous SEE1, which has this weekend? Anyone in here in C1? The 20th, next weekend. Okay. All right, so for C2, well, what's convenient is just since now what's changing is the x, and the x is going from 0 to 1, it would be convenient to let this also be a 1 second t. I just call it second because I always feel like t is a time parameter, okay? But here's the key. There's two things. One, these have to be consecutive or continuous, and two, they cannot overlap. Actually, there's three things. And t, the location of our point at this t equals 1 must be the same as the location of our point at this t equals 1. So does anyone want to give it a shot? Maybe you're following along in your book. What's x doing? It's going from 0 to 1. So what do you think x equals in terms of t? T minus 1. T minus 1, yep. Practicing doing that. Okay, so let me make sure that's right. X equals T minus 1. So where is that at T equals 1? What does X equal? 0, good. And where is that at T equals 2? 1, okay, that's what I want. What does Y equal in this little curve? It just always equals 2. Okay, and what does Z equal? Okay, so for the next one, notice we need Z to change, so it still looks like it's convenient to let this T be a 1 unit space. Now let me tell you something. If you decided to make this, sorry, that should be a 2. If you, for some reason, decided to make this from 2 to 4, that would affect this right here, and that would totally take care of the parametric difference, and when you popped it in, it would still work. So Shiva, to answer your question, these are not unique equations, but they satisfy what we need. Okay? It's crazy, but it works itself out. I could have a different set of parameters for a different definition of my parameter variable, different set of time. Okay? All right, let's stick with what we're doing. What does X equal? And Y? And now Z. We want it to start at 1. We want it to start at 0. So at T equals 2, we want Z to be 0. And at T equals 3, we want Z to be 1. So T minus 2, I agree. And that's our first example of the day. No calculus yet. Just very difficult conceptually to, what's that word say? Parametricize. Okay? All right, so we're going to skip the limit definition and just kind of give you, all right, so it looks like this. Notice that they're called line intervals, and this C, I think, refers to the curve, okay? And I'm just going to stick to the three-dimensional one for this, even though we can do it either one, okay? I know you're already intimidated by that. Don't be. Once we do an example, you'll feel better of this. But, so these are all the parametric equations we just figured out. Okay? And then what we're going to multiply by is, what notation do they use? Okay, now I want... Okay, I'll explain in just a second. Okay, here's what you're doing, okay? Imagine that there is a force field, okay? That force field is determined by some multivariable equation, okay? Now, you also have a curve, which is determined by some set of parametric equations. Okay? Now, let's assume that this force field actually represents change in density throughout the field. So at each point on this curve, the density is different. Okay? Then at that point, if this little curve had a uniform radius with a changing density, what you would be doing is adding up all the products of density times length, and that would give you mass. Because in length in this terms is actually volume. Because it's got a 1 unit diameter. It's like the planar lamina again. We're using that as an example that you might understand so that we can eventually go further than that. Okay? Yes. Now, you might be wondering, why is this length? Hey, remember when we were doing parametric equations, we were doing the components of acceleration. So the centripetal component and the normal component of acceleration. And remember how it was convenient to find arc length if we turn these as a parameter of s. And remember how we kind of skipped that and we were like, no, we're just going to do it by doing it the same way we did in BC calculus, which was like distance is the integral of 1 plus f prime of x squared. Remember that? There was an alternative way to do this, and it was f prime of s. No. F sub x prime of s plus f sub y prime of s squared. It was like that. See, here's the problem. We skipped that because it confused me. We went over it. You went over it with the class, the other class. But then I was like, I've never seen that before. I don't think it's important. But why hadn't I never seen it before? Because I never really understood line integrals well enough. So next year we won't skip that part. But this year we did. We can't go back. Okay? You got it? All this is density times length. If you can understand that, you can do this chapter. Okay? So let's do an example and it will make way more sense. So let's do the line integral. That's what this says. It looks like a curve integral of x squared minus y plus 3z. Is that the right one? Yep. Plus 3z ds. Okay? Where c is this thing. So c is a vector, or it's a straight path that goes from the origin to the point 1, 2, 1. Okay? So, let's define c. Well, we only have to worry about one integral from t. So what would be the easiest integral we could come up with? 0 to 1. And what does x equal during that interval? X equals t. What does y equal? 2t. Right? And what does z equal? T, right? Does everybody get that? So what's x prime of t? And what's y prime of t? And z prime of t? We're going to need those. Okay? So here's what we do. We change that. What's our limits on t? It goes from 0 to 1. What's x in terms of t? X is t. So now this becomes a t squared minus 2t plus 3t, We've changed. Now, look, I hope that you understand what this thing is right here. That's a function of how many variables? 3 variables. So what this represents is a varying scalar over our axis. Meaning, as I put in a different x, y, and z, forget about the integral. Just forget about the integral. Just look at this function. As I put in different x, y's, and z's, I get different outputs. Think of that output for now as the density. Do you understand? But we took that density equation and wrote it in terms of t, because now, as we take that density and multiply it by length, we get something that's useful. So our length is 1 squared plus 2 squared plus 1 squared. Right? Got it? So what do we get? The integral from 0 to 1 of t squared plus t times radical 6. So it's t cubed over 3 plus t squared over 2 as t goes from 0 to 1. So it's radical 6 times 1/3 plus 1/2. Why did I think that was a minus? It's not. Okay, so it's radical 3rd times 2/6 plus 3/6 times 5/6. So it's 5 radical 6 over 6. And since we did this as an analogy the entire time, I want you to understand that means that that wire, which has a length of radical 6, but has variable density, weighs 5 radical 6 over 6 units. Okay? This green line is only there to help you understand that this vector is coming towards you. It's to give you perspective. It means nothing. It means that the tip of this wire is directly above the point 1, 2, 0. That's all it means. Okay? Great question. All right, example 3. Let's evaluate the line integral of x ds, where c equals c1 plus c2. And there's C1, and there's C2, okay? So what do we have to do first? Yes, we've got to establish some parameters. So for C1, I know I can do that one. C2 seems like it's going to be harder, okay? What's our value for T? T goes from 0 to 1. X equals T, Y equals T, okay? For C2, it seems to me like it makes sense to go from 1 to 2. I'm looking in the book to see what they did. Okay, so if you're one of the 4 people in the world that are watching this video, then what we're going to do here is make kind of a contradiction to something we said earlier. Okay? And it's because of simplicity or ease, our own ease sake. What we're doing here is we're traveling along this path, and then traveling along this path. That's C1 and C2. We've already defined our path and parameters for t here for C1. I don't like this because I don't like being in two different places at one time. But what's easiest for us to do is understand that we are taking the line integral of two completely separate curves or paths, and then we're going to add them up. And the sum of that is going to be this. Okay? So to make it easiest on ourselves, we are going to repeat our parameter. And if you remember from way earlier in the year, I didn't like it when we did this earlier either. Okay? But it makes more sense to me now. So we still got to figure out, okay, how do we get from 1, 1 to 0, 0 along this path? Well, I think we just let x equal something kind of easy. So what would x be to get us at 1, 1? That's right. I think it'd be 1 minus t, or is it t minus 1? Yep. Let x equal 1 minus t. Okay? Well then, since y equals x squared, then what does y equal? 1 minus t squared. Okay? Okay, so now, to get that, we need to split it up. X. So x is 1 minus t. Alright, so what is dx dt? Or x prime of t? Negative 1. And what is y prime of t? Negative 2 times 1 minus t. So 2t minus 2, right? Okay. Got it? So, it's the integral from 0 to 1 of 1 plus 2t minus 2 squared dt. That's just C1 though, right? So what would C2 be? Yes, sorry, this would be C2. Yes. And C1, what would C1 be? Same integral, or same interval, t times radical 1, right? No. No. 1 plus 1. Right? And we just need to add those up. Alright, so let's do C1 first. It'll be easier. So radical 2 times t squared over 2 as t goes from 0 to 1. So it's radical 2 over 2. Okay? And then up here, we got, this is going to take a lot of space. Yeah, we'll probably do that in our calculator. You're right. Let's just expand it just to see what it would look like. 1 plus 4t squared minus 8t plus 4. Okay? And then at that point I would just put it in my calculator. You're going to be doing a lot of that. And you get 5 radical 5 over 12 minus 1/12 from our calculator. we've already, minus 1/12. Why don't you we'll just write the answer as a decimal, okay? So the answer is this plus that, and you get about 1.56. Is that right? Seems too low. Yeah, I guess it's just radical 2 plus a 12th, right? Isn't that what it comes down to? Oh, no. Okay. The density is always less than 1? Oh, yeah, because x represents the density. Our x is never bigger than 1 in this. So here there's no density. Here there's very little density. Okay, that makes sense. Excellent, Shiva. And that's where we're going to cut this off, because 26 minutes is enough. Boom.